Hello everyone, my name is Diksha and I am from the Bodhi Academy. Today I am going to continue with the HALOALKANES HALOARENES chapter, that is the organic chapter from standard 12th. So we will do some nomenclature examples today. So this is a question in which we have names of the compounds, we have to draw the structure. So if you consider the first one, 2-chloro-3-methyl pentane, how to go about the structure that we will see here. See, 2-chloro-3-methyl pentane. First thing you will do is just observe the name, okay, that is suffix through which the name ends. So pentane is the suffix. So pentane means how many carbons? 5 carbons. So that you have to do first. So how many carbons we have to draw? 5. 1, 2, 3, 4, 5. Pentane. Then look here. 2-chloro-3-methyl. So now you start numbering from anywhere, this side or this side. So if I number from this side, it will be 1, 2, 3. So at second position I have chlorine. Third position is methyl group. So CH3. Okay. This is the second step, and last step you have to just add hydrogens to each carbon. So CH3, CH, CH, then CH2 and CH3. In order to maintain the valency, you need to add accordingly the hydrogens. Okay. So this is the way to draw the first structure. Second is 1-chloro-4-ethyl cyclohexane. 1-chloro-4-ethyl cyclohexane. Now what is cyclohexane? Cyclohexane is this hexagonal ring without bonds. So this is not a benzene, okay, without double bonds. This is cyclohexane. Now in cyclohexane, what we have at first position, we have chloro. So let us write here chloro, Cl. And at fourth we have ethyl group. So 1, 2, 3, 4. So fourth is C2H5, which is ethyl group. So this is the structure of 1-chloro-4-ethyl cyclohexane. This is how you have to draw the structures of the compounds, okay, whose name is given. Then nature of the carbon halogen bond. Now how is the nature of the carbon halogen bond? So carbon is more carbon is positive, okay. When you have CX bond, you can observe that C exhibits partial positive charge and halogen exhibits partial negative charge. So there exists some polarity between the CX bond. So what happens here, as you go down the group, size of the halogen atom increases. That means chlorine, fluorine, chlorine, bromine, iodine. So fluorine atom is the smallest and iodine is the largest. So this carbon halogen bond length also increases as you go from up to down. The bond length also increases, and some typical bond length are given here. So methyl fluoride, its bond length is 139 picometer, which is less. Then CH3Cl, methyl chloride, it's 178, which is more than methyl fluoride. Then 193 is of methyl bromide, which is more than them. And last, the length increases up to this iodine, which is 214 picometer. Okay, now you have to understand that here, okay, bond length, okay, if bond length increases, bond strength decreases. So bond length and bond strength are inversely proportional, which you have already studied in 11th standard. Let us start with the very important concept here, that is methods of preparation of haloalkanes. So first of all, we will see how to prepare them from alcohols. First of all, we take alcohols, okay. Alcohol when added to HCl and zinc chloride, and this is together called as Lucas reagent, okay. When this is added, when these are the reaction conditions, we get alkyl halide plus water. Then alcohol when treated with sodium bromide and sulfuric acid, it gives alkyl bromide. Now when you take specifically this reagent, you will get specific halide only, that is chlorine, bromine. But in third reaction, you can observe that alcohol is treated with PX3, phosphorus trihalide, In this, whatever halide you want in the product, that you can take here. So it may be chlorine, bromine, fluorine. We don't carry out such reactions because it is the reaction is very violent, and iodine gives very slow reaction. So most of the times we consider only these two, chlorine and bromine. So when you have specific chlorine or bromine, you have to take alcohol plus phosphorus trihalide to give alkyl halide. Then alcohol plus PCl5 gives alkyl chloride, and alcohol plus red phosphorus along with halogen, that is halide, that is bromine or iodine, it gives alkyl halide. And last reaction is alcohol when treated with thionyl chloride. Alcohol plus thionyl chloride will give alkyl halide and sulfur dichloride and HCl. Then next is from hydrocarbons. From hydrocarbons we can prepare, first of all, from alkanes by free radical halogenation. Okay, so here we basically take chlorine to carry out the reaction. What we do here is we take hydrocarbon, that is alkane. Okay, here we have taken butane and butane. Butane when treated with chlorine and UV light or heat, it gives us mixture of two products. One product is having chlorine, the first carbon, and second mixture we are having chlorine attached to the second carbon. Okay, now here we have chlorine attached to first and chlorine attached to second. So we get a mixture of these two products when we treat in the UV light. Then from alkenes, if you have symmetrical alkene. Symmetrical alkene means either side of the double bond we have same condition. So here we can see same conditions we have. So this is symmetrical alkene. When we add hydrogen halide to it, okay, for example hydrogen chloride, hydrogen bromide, hydrogen iodide, what we get, hydrogen will go and attach to one of the carbon, and halogen will go and attach to one of the carbons. So and bond will break. So we get this type of compound here. One hydrogen and halogen will go and add to the respective carbon. Now when we have unsymmetrical carbon, this follows Markovnikov's rule. Now we have studied this in our 11th standard hydrocarbons chapter, Markovnikov's and anti-Markovnikov's rule. Now what Markovnikov rule states, if you have an unsymmetrical alkene, okay, for example see this is unsymmetrical alkene. To that if you add HI, HBr or HCl, then whatever halogen we have or negative part we have, that will go to the carbon having less number of hydrogen, and hydrogen will go to the carbon having more number of hydrogen. So here the major product is the one where we get iodine attached to the middle carbon. So here iodine attached to the middle carbon, hydrogen attached to the last carbon, and here iodine attached to the last carbon. So this is minor product. Okay. Then addition of halogens. Addition of bromine in carbon tetrachloride to an alkene resulting in discharge of reddish brown color of bromine constitutes an important method of detection of double bond. So this method to treat alkene with bromine and carbon tetrachloride is used, and it is detected by discharge of reddish brown color, okay, which detects the double bond in the molecule. So we get vicinal dibromide, and if you have this present, then it have a double bond. Next very important reactions from this chapter are halogen exchange reaction. So there are two name reactions under this, which are Finkelstein's reaction and Schwarz reaction. So let us see first Finkelstein reaction. Now what is Finkelstein reaction? We have to take alkyl halide, add to it sodium iodide, okay, sodium iodide and dry acetone. Okay, so alkyl halide or alkyl bromide with treated with sodium iodide in dry acetone, then it will give alkyl iodide. So how you can remember, Finkelstein reaction is basically performed to prepare the alkyl iodide. Only iodide, alkyl iodide we can prepare from this, not other alkyl halides. So here we may have other alkyl halide, that is RCl, RBr, but in the product we should get only this RI, that is alkyl iodide. Okay, so how you have to remember this? Remember the name along with the reagent. So Finkelstein reaction, that means dry acetone and sodium iodide, and iodine will get replaced over there. Next similar reaction is Schwarz reaction, but here fluorine gets replaced. So here we have CH3Br, methyl bromide. To that we can either add silver fluoride, mercuric fluoride, cobalt fluoride, or antimony fluoride. Okay, so these four reagents we can use to carry out Schwarz reaction, in which fluorine will get replaced. Then preparation of haloarenes in this from hydrocarbons by electrostatic substitution. So here what we do, haloarenes means to the benzene ring or to the aromatic ring there is halogen attached. So what we do, we take here our general this toluene compound. To that we add halogen halide. Okay, so after adding that, we maintain the conditions as iron and in presence of dark. So when we treat toluene along with halide in presence of iron and dark, we get orthohalotoluene and parahalotoluene. That means we get a mixture of ortho and parahalotoluene. Halogen gets attached either at ortho and para position, so we get a mixture. But the major product here will be para, like always. Then the next very important reaction is Sand-Mears reaction. In that we take aniline. Aniline is taken. Okay, aniline is treated with sodium nitrite. So this is sodium nitrite and hydrogen halide at 273 to 278 Kelvin. So we get intermediate, that is benzene diazonium halide, which is further used to produce the product. So here we get benzene diazonium halide by treating it with this reagents. If I have Cl over here in place of X, then I get Cl here, and that is called as benzene diazonium chloride. Then this intermediate is taken. Now this intermediate is very important because it is used to carry out different reactions to obtain the products. So benzene diazonium chloride when treated with cuprous halide. So if I want here chlorine, then I will take cuprous chloride. If I want bromine, then I will take cuprous bromide. So you have to take this way, and then that particular halogen will get attached to the benzene ring. So if I take chlorine here, then chlorine, and here also chlorine, so I get chlorobenzene. One thing we have to remember here is when you have to replace the iodine here, then we can't use this cuprous iodide here. So here we have to take potassium iodide. So Sand-Mears reaction. So this intermediate when treated with Ki, potassium iodide, we get iodobenzene, and along with that N2. So for iodine only we have this exception, and chlorine and bromine follow same procedure. Then talking about their physical properties, they are colorless when they are pure, and bromides and iodides develop color when they are exposed to light. Then about melting boiling points, here since they have polarity, their melting boiling point will be higher. So due to greater polarity as well as higher molecular mass as compared to the parent hydrocarbon, intermolecular force of attraction, that is dipole-dipole and van der Waals, are stronger in halogen derivatives. So boiling point of chlorides, bromides, iodides are higher than those of normal hydrocarbons. Now when molecules get bigger in size, they have more attractions, and pattern of variation of boiling point is shown here. So we can see that now red is chloride, blue bromide, and yellow is iodides. So we can see that as you increase the size, boiling point also increases. So alkyl iodide is having more boiling point than bromide, chloride and fluoride. Now what is the reason behind this? Because with increase in size and mass, the magnitude of van der Waals force also increases. Okay, then this is very important, that branch chain and straight chain compound. So you can see here, having same formula, these are the three compounds, these are the isomers. Okay, so this is a straight chain, this is a branch chain, and this is more branched. So we can see that straight chain is having higher boiling point as compared to small branched, as compared to largely branched. So why this is so, like what is the reason for having higher boiling point or melting point in the straight chain compounds? Now this is because with branching, what happens when you branch the compound? Surface area decreases. Okay, so when surface area decreases, it try to attain the shape of the sphere. So when it try to attain the shape of the sphere, there are less attractive forces between them, which are weak forces. So whenever there are weak forces, there will be less temperature required to boil them or break the bond. So that's why boiling and melting points of branched compounds are lesser than straight chain compounds. Then one more thing about ortho and para, that is boiling points of isomeric dihydrobenzenes are nearly the same. However, para isomer are high melting. So you can see these are the three examples in which this is a para. Okay, this is a para arrangement, and in these three you can observe that this is a symmetrical arrangement. So why we have para group more melting point or more boiling point? So para isomers are high melting as compared to ortho and meta. This is because of symmetry of para isomers that fits in the crystal lattice. So this symmetry fits in the crystal lattice perfectly. That's why it is difficult to break the bonds. Then about their solubility, they are very slightly soluble in water. They are not that much soluble in water because they cannot form easily bonds with water. Okay, so solubility of haloalkanes in water is low. Then about reactions, first of all we will see nucleophilic substitution reactions. So in nucleophilic, what is nucleophilic substitution reaction, that we have to understand first. Nucleophilic substitution means nucleophile. Nucleophile we have learned in 11th standard. Nucleophile is the species which have negative charge or which is nucleus loving. Okay, so which will always have negative charge. So nucleophile attacks to the carbonyl carbon, or nucleophile attacks to the carbon which is further attached to functional group, and then that halogen leaves and that nucleophile gets attached to the carbon. So this way we have many nucleophiles: OH, H2O, OR, I minus, NH3. These are the nucleophiles. Groups like cyanides and nitrites possess two nucleophilic centers and called as ambident nucleophiles. Now in coordination chemistry we have learned what is ambident. Okay, ambident means which can attack or which can link through both two atoms. Okay, two different atoms. So here we can see there is a negative charge on this carbon, and here there is a negative charge on nitrogen. So linking through two different atoms. Okay, so we will see a general mechanism for this reaction, substitution nucleophilic bimolecular reaction, and this is called as a SN2 reaction. Now why this name is given SN2? Okay, so that we will see. Now substitution nucleophilic bimolecular. Now this bimolecular words tells that rate of this reaction depends on the concentration of both the reactants, meaning two reactants are participating in the reaction and rate of the reaction depends on both the reactants. That's why it is called as the substitution nucleophilic bimolecular reaction. So then the reaction between methyl chloride, hydroxide ion to yield methanol and chloride follows the second order kinetics. So second order kinetics, that means the rate depends on both the reactants. So let us see how it attacks. So nucleophile, when is combined or when is treated with alkyl halide, simple alkyl halide, that is methyl chloride, this nucleophile attacks to this carbon, okay, on this carbon, and this will now try to join, or it will try to link to this carbon, and at the same time chlorine will try to leave from here. Okay, so this is an intermediate in which both the chlorine and the nucleophile is shown. One is coming to attach and other is leaving the carbon. So that's how we get this product, that is OH getting attached to the carbon and chlorine is leaving. So Cl minus. So this is the stereochemical way of presenting the mechanism of the SN2 reaction. Now what are the important points here that you have to remember? That this occurs in a single step. This is a single step through which it occurs. Okay. Then one more thing, after carrying out the reaction, okay, stereochemically the process is called as inversion of configuration. That I will show you all how it happens. See, whenever you attack nucleophile on this carbon, chlorine is on right hand side, okay. Okay, after attacking this, OH comes and OH also joins. So OH then is shown here at the left hand side. So whenever you attach the nucleophile in SN2, there is an inversion which takes place. That means observe this and this structure and you will understand how the inversion takes place. So if OH would have attached to the same place where the Cl is, it is not an inversion. Now OH is attached to the opposite place where the Cl is attached, it is called as an inversion. So in SN2 there is an inversion takes place. Okay, reactivity, who will react more towards SN2? So primary halide reacts more towards SN2, then secondary, then tertiary. So primary means before primary we have methyl halide, so CH3X. So CH3X will react more towards SN2. Okay, now why this is so? Because when you have simple methyl halide, there is no steric hindrance, okay, which will cause a hindrance to the incoming nucleophile to attach to the carbon. But whenever there are more and more groups, they cause steric hindrance. That's why when you have simple methyl group, nucleophile will get attached easily. That's why the order is this way. Next is substitution nucleophilic unimolecular, that is SN1 reaction. In SN1 we can consider that SN1 is the substitution nuclear unimolecular, which is, the meaning is the rate of reaction depends on concentration of only one reactant. Okay, so here there are two steps which are occurring in this SN1 reaction, and first step is when you have to take the compound alkyl halide, and this is a slow process, so it is reversible and it will produce carbocation, okay, carbocation and bromide ion. Then that carbocation is treated with nucleophile in step 2 to get the product. Now here the order is exactly opposite to that of SN2 reaction, because here there is a generation of carbocation, and since tertiary carbocation is more stable than secondary, primary, we have order in this way, that is tertiary is more stable, then secondary, then primary. Okay, and here there is a racemization take place of this process. Okay, here there is no inversion, so racemization takes place. So here they have given the order of stability or order of reactivity for SN1 and SN2 reaction. Then stereochemical aspects of chemical nucleophilic substitution reaction. So here we have optical activity, chirality, retention, inversion and racemization. Now what is optical activity? Optical activity means whenever there is a plane of polarized light produced by passing an ordinary light through the Nicol prism. Now this is the way to produce the polarized light. Now when it is rotated, it passes through solutions of certain compounds, and those compounds are called optically active compounds. So the compounds which can optate this polarized light towards left, they are called as levorotatory, and the compounds which can rotate this towards right, it is called as dextrorotatory. So these are the end. For levo, negative sign is assigned, and for dextro, positive sign is assigned. And they are called as optical isomers. Okay, optical, and the phenomena is called as optical isomerism. Then molecular asymmetry, chirality and enantiomers. So molecular asymmetry means the compounds which are not symmetrical, okay, that comes under this. So we can see these are the simple examples. An object that cannot be superimposed in its mirror image is called as chiral. So if you look at the hands, okay, our hands, then we cannot superimpose them. So that's why they are optically active, which is chiral. Okay, chiral means they cannot be superimposed on each other, even legs. But this objects we can superimpose. This non-chiral objects, they can be superimposed. Then yeah, this is butane 2-ol. Racemize, or we will see what is racemize. Now I will just tell you what is chiral. So if I have the carbon, okay, this is a carbon. Now carbon is having here Cl, here we have H, then here we have C2H5, and here we have CH3. Then this carbon is having this different group, this is also different group, this is different group. This carbon is having 4 different groups. So such cases, or this carbon is called as chiral carbon. Okay, but if any 2 groups are also similar, it is called as achiral. Okay, for chiral condition you should have all the 4 carbons different. The stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. So the non-superimposable images which are isomers, which are called as enantiomers. Then racemization means what? A mixture containing 2 enantiomers in equal proportion with 0 optical rotation, and they will not rotate the plane of polarized light, and the rotation due to one isomer will be cancelled by rotation due to other isomers. So such a mixture is called as a racemic mixture or racemic modification, and it is represented by DL or plus minus before the name. And this is called as racemization, which takes place in SN1 reaction. Then about retention. Retention of configuration is the preservation of spatial arrangement of the bond to a symmetric center. In simple language, what is retention? See, if I have OH group to this particular compound, OH group is attached to this carbon, and I carry out the reaction, okay, I add certain nucleophile and carry out the reaction. If that nucleophile gets attached to the same position where the OH is, then it is called as a retention. Okay, so we are not changing the positions of that group, so same position, then it is retention. Next is inversion, that we have already seen in SN2 reaction, that if here, okay, here there is a Y group which is attached to this compound, or let us consider X is attached to this compound, and we are replacing the X by Y. So whenever we replace, if that Y comes to the opposite position, then it is called as a retention. So this is retention. If that Y comes to the same position, then it is called as a, sorry, when Y comes to the opposite position, it is called as a inversion. Okay, inversion. So here it is inversion, this is retention, and A plus B, when you get a mixture of these 2 products, both the products, then it is called as a racemization. So in SN2 we can see inversion, in SN1 we can see racemization. So this is the mechanism of SN1 they have given, in which we have this compound, okay, and in that if I treat it with nucleophile, okay, so we will see both the attacks, okay. So here when I attack the nucleophile, okay, it can come through this side, okay, through up it will attack to the carbon, and after attacking it will get attached to this side, okay, and in this case I will attack the OH through this downside, and it will get attached here. So this is what, this is the um, um, dextrorotatory and this is levorotatory. So we can get a mixture of both the products, so that's why it is called as the racemization of the product. Okay, this is the racemization reaction which happens in SN1 reaction. Then we have elimination reactions. In elimination reaction, there is a elimination takes place. Okay, so that is beta hydrogen atom. So let us consider now, this is alkyl halide. When alkyl halide is heated with alcoholic KOH, so what is the reagent here? Alcoholic KOH. What happens? See this reagent and carry out the reaction. So there is a elimination of halogen as well as hydrogen. So there is an elimination of hydrogen and halogen from here. So what happens? One halogen and one hydrogen is removed. Whichever halogen you are removing, the adjacent carbons hydrogen you have to remove. So that after removing, we get double bond between those two carbons and base is nucleophile is bonded to the hydrogen and side product is halogen, and this reaction is called as a beta elimination. And this comes with one rule which is called as Sedgwick rule, in which the rule states that in dehydrohalogenation reaction, the preferred product is that alkene which has a greater number of alkyl groups attached to the doubly bonded carbon atoms. So this is the reactant. Okay, so to this reactant we are adding OH. There are two possibilities now. Okay, since we have double bond here, there are two double bonded carbons. So there are two possibilities that bromine bromine will leave, and there are two hydrogens which can leave. So this bromine will leave along with this hydrogen will leave, or bromine with this hydrogen. Okay, here CH2, so one of this hydrogen. So when this hydrogen is removed, okay, when this hydrogen is removed and bromine is removed, we get this product, pent 2ene. And when this hydrogen is removed, this hydrogen and bromine is removed, we get this product, that is pent 1ene. But which is major, that depends on this rule. Now this rule states that the preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded atom. So here we can see this carbon, doubly bonded carbon atom is attached to one carbon, and this carbon is attached to one here. Okay, or this is attached to two. But here we can see this doubly bonded carbon atom, this is not attached to anything this side, but this is attached to one carbon. So this is less attached and this is more attached. So that's why this is major product according to Sedgwick rule. Okay, and this is minor, meaning this is formed in very less amount. Okay, so with this I finish this part. I will continue with this chapter in the next part. Okay, thank you.